we've seen some examples of the causal functions, and now we will apply these functions to derive an important property of Laplace transforms. So let's say we have a function and we know a Laplace transform of that function. Call it f bar of s. The question is, what would be the Laplace transform of a causal function generated by this s? So if we'll take f of t shifted by time a and multiplied by the unit step function. So that's an example of the causal function. And we want to know what Laplace transform of this function would be. Let's use the definition. So that's one of the rare cases where we would need a definition. So by definition, Laplace transform is an integral of that function and an exponential. And because the causal function does not really exist before a given time, that's why it's called causal, so we take that property to simplify our integral. So we can see that before that time the function is 0 and the integral will be 0. So we can eliminate at least a bit of this integral between 0 and a, and only start from a, not from 0. So now we have the same integral, but starting from time equals a, and we also can, in this case, write unit step function as just a function equals to 1, right? So because it's 1, we can just ignore this factor. And it is helpful to make a substitution in this case. Substitution is just this delayed variable or shifted variable. Or we can write it as the another variable x is t minus a, or t is x plus a, and so on. And then the integral will become that. And we can take an exponential out of the integral because that is just a number. It does not depend on x, so we don't integrate it with respect to anything. And if we look closely at the integral, it is just a definition of the Laplace transform of t or of x, because it doesn't matter, you take a definite integral between the limits, so you can always get the same answer. And that Laplace transform is multiplied by the exponential. And that brings us to our first theorem of this kind, which is called a time shift or a time delay theorem. And it tells us that if you know a Laplace transform of a function, you can immediately find a Laplace transform of a time-shifted version of that function, the causal version of that function, by just multiplying your Laplace transform by the exponential to the appropriate power. What's important to notice here is that you have minus a in the power, you have minus a in the unit step function, and you have minus a in the shifted version of the function. So bear this in mind. That's the time shift theorem. And now we're going to look at another version of this theorem called an inverse time shift theorem, which is literally just going backwards. So if somebody gives you again a function with the corresponding Laplace transform, you can find an inverse Laplace transform of an exponential multiplied by Laplace transform of that function by just going one step back and returning to the time-delayed causal version of that function. So that's nothing than just moving Laplace transform from the right to the inverse Laplace transform to the left, but otherwise it's the same. Example time. You're asked to find an inverse Laplace transform of that fraction. You have an exponential in the numerator and the s squared in the denominator. How to do it? Well, one way to look at the table, but let's do it by using the time delay theorem. So we're asked to find an inverse Laplace transform of the exponential the power of 3s over s squared. And we can write this in equivalent form as inverse Laplace transform of that exponential times a function, Laplace transform of a function, where this function is just 1 over s squared. And by inverse time shift theorem, we have that the inverse Laplace transform of a function multiplied by the exponential will be just the function itself, but shifted to the -3, multiplied by the unit step function shifted by the same amount. So the only remaining bit here is to find out what is this function. And we know that if we have a Laplace transform which is 1 over s squared, then the original function will be what? Yes, that will be just a linear function. And by substituting that function into our theorem, we have that the inverse Laplace transform of this exponential over s squared is just a linear function shifted by 3 times a unit step function also shifted by that amount. And that is the answer to that example.